Hey everybody, today we will do another video and we will continue with transformers a little bit and eventually we will probably do impedance in transformers because I think it's a very important topic, but right now we will work with the basic of the transformer, right? How to do calculations. So like in this case right here, we have this, right? So let's say, we just have an open secondary, right? But we have a transformer that we need to calculate. And in the problem statement, state that we have a transformer if I can get a marker that works, that will be very helpful. But let's try this one. So we need to, if I can find another marker that work, because apparently these markers are dried out. Maybe the weather, because it's too hot over here. But it says, and I'm sorry about that, about the delay. An ideal transformer an ideal transformer is rated 2400 120 volts comma 9.6 kVA and has 50 turns 50 turns on the secondary, right? The secondary side, right? So now calculate A. Part A is asking to the turns ratio. Calculate the turn ratio. Calculate the turn ratio right? So that's one of the problems I need to solve. And B, the number of turns in the primary. B, the number of turns in the primary, right? That's in the primary side. And C, right? Of course. And C, part C, right? The last thing that we need to do is the current rating on the primary. The current rating on the primary and secondary winding, right? Current rating on the primary and secondary winding. So right, so that's the problem statement, right? Now this is the problem statement, right? And how we solve problems, right, in engineering or any type of math problem? Well, first look at the given, right? What is a given to us? So we have a transformer, right, that was given. We have the volt, the primary and the secondary volt rated. We have the kVA, right? And also we have a turn ratio of 50, right? Let me just put it right here so it's more clear. It's 50 turns, right? On the secondary. So now the first step is to calculate A, the turn ratio, right? And B, the number of turns in the primary because the secondary was given, right? Okay, so let's get started, right? So now with that information, let's calculate this, right? So we talked about last time, we said that this was called the iron core, right? This is the primary side, right? This is the primary, this is the secondary, right? And in this case, the primary over here has 2400 volts and 2400 volts, and over here we have 120 volts. Now, so we have the information, and we have the secondary turns, that is 50, over here. Now, if you think about it, look at the rate of voltage in the primary. It's a lot more than 120, which means that tells me that it's going to be a lot higher, the turn ratio in the primary, analytically. That's why when you solve problems and the real life, right, you look at a number, and when you look at a number, you say, okay, does this make sense, right? Is this making sense for what I'm doing. If you see a numbers look totally big or whatever, or too small, and you comparing what the problem statement or whatever the project scope is saying, and they say, oh, let me analyze that because it's not making any sense, and then you take that step to kind of reverse engineer, say that let me just go back and see why this number is not making sense. But I can actually see right now that if this is in the secondary I have 120 volts, this is going to be a lot bigger. It's going to be a lot bigger on the secondary side. But anyway, let's prove it, right? So let's not assume anything. Okay, so first step, right? We calculate the turn ratio, right? So the turn ratio, we can see that of course B1, right, is greater than B2, right? So B1 is actually 2400 volts, which is greater than B2, which is 120 volts. Okay, so that's the first step. Second step, we do the turn ratio by doing the ratio. Well, how does it make more sense, right? Make more sense to put this number on the top and this in the bottom, right? So N in this case will be, turn ratio is going to be equal to B2 over B1, right? B2 over B1, which is equal to 120 over 2400, right? And those cancel out and you get 12 over 240. Now 12 over 240, and that is going to be equal to it's going to be equal to 0.05, right? That's the turn ratio. That's part A right there. So part A is done, right? Now A is done, right? A is done. Now let's do B. So B says, calculate, okay, now B says the number of turns in the primary, right? The numbers of turns on the primary. Okay, so we have the turn ratio, right? We have the turn ratio. So we can actually use the formula that we can say that lowercase n, right, is a turn ratio is equal to B2 over B1, right? Okay, actually no. It's the same thing but different letters, I'm sorry. It's N, capital N2 over N1. Okay? It's basically the same thing, but I am using, because I already did that, now I have to do this because I already have this guy right here. I need to calculate this because I have it the secondary, right? Now what we do? What we do now? Well, you go across, let's do the little algebra thing that we learned back in the days, right? Maybe 5th grade math or 4th grade, I don't know. So let's do that, and let's do that. N1 is equal to N2 divided by n small n. So N, capital N, capital N1 is equal to N, capital N2 divided by a small n, right? Now let's substitute the numbers. Let's substitute the numbers now, okay? So N1, capital N1 is going to be equal to what? 50 is equal to 50 divided by what? The small number that I got, right? Because that was my small n. My small n was a small number. Right? So let me just by 0.05. And of course, let's take 50. And it's equal to 1,000 turns. See? I told you, say it from the beginning. Is equal to 1,000 turns. Right? You can see that it's a lot, it's a bigger number. It's 1,000 turns comparing to 50 turns. Okay. Now that is part B. Right? Part B is done. Right? So let's do A. Let's put the for A. A is what? A is, okay, so A is equal to 0.05. B is 1,000 turns, right? And now I'm looking for C. So let's do C real quick. So let's look at C and see what is So now let's look at C and see what is going on, right? So for C, we're looking for the current, right? And how do we calculate the current? We can actually do a couple different ways, right? And this is easy because we have this. We have this guy, and we have this guy, and we have this guy, right? We say last time that power in is equal to power out. If power in is equal to power out, then we actually can take these numbers and calculate the current coming in and the current coming out, right? The current coming in the primary, as you can see, you can actually see analytically again, by analyzing this, you can see that the current in this area, in this side of the transformer is going to be higher. It's going to be higher. The smaller is the voltage, the higher is the current. And the larger is the voltage. Okay, the smaller is the voltage, the lower is the voltage, the higher is the current. The higher is the voltage, the lower is the current. Okay, so let's keep that in mind. Okay, so let me okay, so let's do it right here, right? So we do in part, so we done part A, we done part B, right? So Now let's we done this. So let's knock this out a little quick. Okay, so let's do I1, I the primary, is equal to what? Is equal to power over B1, right? I1 is equal to power over B1, which is equal to what? Which is equal to 900, okay, so it's 9,600, right? Divided by 2,400. 2,400 volts. And that and I hope this makes sense because power is equal to voltage times the current, right? I don't have to manipulate this again. So power is equal to voltage times the current. When you do this, you have the power is equal to I times voltage, right? So I already simplified that into that. So divided by 2,400. It's a very low current. So now we have what? So we have I1 equal to what? Is equal to 4 amps. 4 amps, right? 4 amps. Very low current on the primary. Make sense? So next we do the secondary. Same thing, right? Now analyzing this is going to be a lot more current in the secondary, which makes sense, right? So I2 is going to be equal to 9,600 divided by 120, right? You can actually do that, and then you can have 960 over 12. So now you get an 80 amps. So this guy right here is I2 is equal to 80 amps. So as you can see that just by analyzing the problem ahead of time, you can actually see where you're going with the problem, right? And that's the kind of experience once you have been doing this, and I mean, it's becomes kind of natural for you to kind of think that way. But that's how you calculate the secondary and the primary currents of a transformer, and then in this how you calculate the ratio, right? So this is, one of the problems that I want to go through about calculating the turn ratio and calculating the secondary and the primary, and this, and the numbers of turns, which is an important, another number is going to be important, and probably eventually I am going to be working on it. It's going to be impedance. Because when you look at a transformer, you have impedance, you have a certain amount of impedance, right? Like resistance, that is, and because even though this is coil, is conductor, but it still have a small amount of impedance, and that is another important concept in the transformers. So I hope you enjoyed this video, and if you like this video, give me a thumbs up. Thank you for watching, and I see you in the next video, and God bless you.